This meeting is being recorded.
Okay. Very good afternoon. Screen is visible.
Yes, sir.
Okay, fine. So what we have discussed in the last lecture, right? We have started with the unit number 3. Then it's syllabus, whatever the points we are going to discuss under this unit. Then we have discussed about the combinational, right, versus sequential logic design. Then overview of this entire unit. Then what do you mean by static CMOS? So what do you mean by static CMOS? So at every point in a time, each gate output is connected to either VDD or VSS, or you can say to the ground, right? This is the first uh, property. And second, you can say the output of gates assume at all times the value of Boolean function implemented by the circuit. So output of that gate, okay, it is assumed as a any kind of boolean function. And second one, output of the gate is connected to either VDD or VSS. If these two conditions satisfy, you can say, or these are the specific conditions to identify the static CMOS circuit, right? Then what are different parameters that you should consider uh, uh, or to analyze the digital gates? So first you should consider its area and complexity. Then you should consider the performance. Then you should consider the power consumption. Then you should consider the robustness and reliability. And as you know, the robustness and reliability, or you can say it it could be analyzed by the static analysis, right? Static analysis of that. That means different vi characteristics and all that part. So it comes under a static analysis that will tell you how robust system is or how reliable system is, right? And to study or to analyze the performance, you should go for dynamic analysis. Okay, so remember this thing. Then we have discussed about the CMOS complementary metal oxide semiconductor. Then it has a pull up network and pull down network, as you know. So this pull up network is basically formed, uh, this pull up network is of only PMOS, and this pull down network is basically of NMOS. Again, you know, uh, why we have combined this NMOS and PMOS, right, in the form of pull up network and pull down network, right? So this pull up network and pull down networks are actually dual networks. Okay, now see, the reason is well familiar with you. Why we have did this is, as the PMOS had some advantages and it has some disadvantages. What is advantages of PMOS? It can pass strong logic 1. And what is disadvantage? It cannot pass strong logic 0, means it passes weak 0. That is about the PMOS. Exactly reverse is the case with the NMOS. What happens with NMOS? In case of NMOS, it has advantage that it can pass strong logic 0 but weak logic 1, right? Strong logic 0 but weak logic 1. So that is kind of advantages and disadvantages of NMOS and PMOS. Now if you combine this, or if you connect in series or in parallel fashion, what happens is the disadvantages of each other can be compensated by each other, and that forms a robust network or robust design, and that is the CMOS, right? So this part also we have discussed. Then we have discussed about what happens when we connect the NMOS transistor in series or parallel connection. So basically NMOS in series, that forms the AND operation. It's a kind of ANDing operation. A dot B is equal to 1. And when you connect it is in a parallel fashion, it's a kind of OR operation. Okay, so It's a and it's a or operation. So basically the uh, series connection, you can say it's a and operation, and the parallel connection, you can say it's a or operation. Okay, so same is the case with the uh, this PMOS, right? So series is nothing but the and, parallel is nothing but the or operation. Okay, you can check here also. In case of series, see, if you apply here both 0, that means what, this both gate will be in a conduction mode. So the whatever the value at x can be transferred to the y. Okay, this is the series. That means what, a and b, that means both gate should be in a conduction mode to transfer the input towards the output. That is the ANDing operation. But in case of parallel, either anyone, either a or b, it is on, then also you can able to transfer this x value to the y, right? You can able to transfer this x value to the y. So this is about the series and parallel combination of the NMOS and PMOS, right? Now next part that we are going to study is a complementary CMOS logic style construction. So now you are well familiar with the CMOS. Okay, it is a combination of PMOS and NMOS, where the PMOS acts as a pull up network, that is PUN, and NMOS, it is acting as a pull down network, that is PDN. Okay, so this pull up network and pull down network are actually, these are actually duals of each other, right? These are actually duals of each other. How you can prove this? You can prove this by using De Morgan's theorem. So in case of a plus, that means it is a or operation, right? A or b bar is equal to AB bar, that means A and B bar, and A and B bar is equal to A bar plus B bar. That means what, this if you analyze by using this De Morgan's theorem, you will come to know that this pull up network and pull down networks, these are dual of each other, right? These are dual of each other, and the complementary gate is nothing but the inverter, right? So the complement means what, the inverting operation. So implements, it can implements any universal gate, any basic gate you can implement using this CMOS, complementary CMOS. Now next part is design of different combinational circuits, design of different combinational circuits using the CMOS. Now this is very important and crucial point. So how actually we are going to design? So let us take an example of NAND gate. Okay. Now tell me, what is truth table of NAND gate? What is truth table of NAND gate? It is exactly opposite to the AND gate. What is truth table of AND gate? Except all one, rest of the outputs are zero. Reverse is the case with NAND gate. Except one, all outputs are 1. That means for only 1 combination, you will get a 0 output, right? As shown here. For this 1 combination, you will get 0. And for rest of the combination, you will get 1, right? You can check any combination. So this 0 1, you will get 1. This 1 0, you will get 1. This 0 0, you will get 1. But for this 1 1, you will get 0, right? For this 1 1, you are getting 0, right? So this is the truth table of NAND gate. So how we are actually implementing using a CMOS? So as you know, the it's a when you talk about the CMOS, it's a kind of pull up network and pull down network. So pull up network has to be of a PMOS, and this pull down part has to be of a NMOS, right? So this A plus B bar, right? If you analyze this using the K-map equations, right? So this pull up network has to be connected in a parallel fashion, And exactly reverse of that is the series fashion. Why series? Because these pull up and pull downs, these are the dual of each other. If one is a in a parallel, or it's a plus b bar, then exactly opposite will be the a and b, because these are the duals of each other. So finally, this pull down network, it is connected to the ground, right? So this G will be A and B bar, and this pull up network is a bar plus B bar. But again, if you solve this, you will get AB bar, right? You will get AB bar. Now you can check its operation here also, whether actually this is behaving as a uh, NAND gate or not. So for just check for this 0 0 condition, right? For this 0 0, what is the expected output? 1. So A is a 0. Now first we will study this pull up network. So A is a 0. That means what? A is a 0. It will be 1, right? B is also 0, so it will be 1. So these both PMOS are in a conduction. These both PMOS are in a conduction. Now coming to the pull down network. So A is 0, that means this upper NMOS is off. This B, this NMOS is also off. Means what now? This VDD will pass towards the output, and that is the 1. That is the 1. Consider the other case. Okay, consider the 0 1. That means what? This uh, A is 0 and B is 1. This 0 1 case, what is expected output? It should be also come 1. So now A is 0. Okay, consider this A is 0. That means what? Now this PMOS is in conduction, right? A is 0. That means this PMOS is in conduction. B is 1. So this 1 will get converted to 0. That means this PMOS is not in conduction. That means only this PMOS is a closed switch, and this PMOS is a open switch. Okay, fine. This is about the pull up network. Now what happens with pull down network with this condition A0 B1? So as this A0, right? So this A0 means what? Now this total gate will be open switch, and this B1, right? So this PMOS NMOS is in conduction, but it is nowhere connected to the output, because this the intermediate NMOS is a open switch. So though it is a closed switch, but it is nowhere connected to the outputs. Now who is connected with the output? This PMOS, right? This PMOS is connected to the output. So it will transfer that VDD towards the output, right? And you will get 1 as a output. You will get 1 as a output, right? So this is about the AND gates, sorry, NAND gate circuit. Okay. Now similarly, you can study for NOR gate. Okay. Similarly, you can study for this NOR gate. So what is first? Now tell me, what is a truth table of NOR gate? It is opposite to the uh, actually opposite with the OR gate. Okay. Will you do this right now? Okay, now I have explained the NAND gate part. Okay, so now you explain, any one of you can explain this NOR gate part, how this outcome or how this circuit will act as a NOR gate. Okay, first write down truth table, then check the conditions. Okay, and then uh, tell me the explanation. Okay, I will give you 5 minutes. Yes, you can continue. Everyone, okay, those who are present in the meeting, please do this exercise. It's important so that you can understand the things uh, very well. First write down the NOR gate truth table, right? And for that particular inputs, check whether you are getting the proper output or not. Okay, do it. I will give you 5 minutes. audible? Am I audible?
Yes, sir.
Okay, do it, do it. Let me just do one thing. Okay, yes. Now you can. Any one of you can explain. Okay, now first tell me what is truth table for the NOR gate,
1000.
right? That means you can say except 00 for rest of the combination, you will get zero output, right? Except 00 for rest of the combination, you can check. See, 00 only you are getting one. For 01, you are getting one. For 10, you are getting zero. Sorry, for 001, you are getting zero. For 10, you are getting zero. And for 11, you are getting zero. That means for only for 00, you are getting one. Okay, now we will check here also. Now only first we will tally this case also. So A is a 0, B is a 0, and now you should get 1. Okay, check here. Now A is 0, that means yes, this PMOS is in conduction. B is also 0, that means this PMOS is in conduction. A is 0, this total uh, NMOS is open switch, that means not in conduction, and this NMOS is also not in conduction, right? This NMOS is also not in conduction. So what you can say, is the output is connected with VDD. Why? Because these both PMOS are in conduction, and that's why you are getting one as a output, right? That you are getting one as a output. Okay, now check for any other condition. uh, Now check this 1 1 condition. Okay, A is 1, B is 1, right? You should get zero output. Now A is 1, that means what? This total PMOS is open switch or not in conduction. B is also 1, so it will go at the gate, it will apply as a 0, so this PMOS is also not in conduction. Now for check for this pull down network. This both is in conduction, right? It is 1, so it will in conduction. So this B is also 1, so it will in conduction. Now means what? Now this VDD is disconnected from the output, and now output is connected with the ground. That means now this 0 will pass to the output, and that's why you are getting 0 as a output, right? You are getting 0 as a output. You can check all cases, right? For this all cases you are getting the uh, that particular output, right? For 0 0 you are getting the 1, for 0 1 you are getting the 0, for 1 0 you are also getting the 0, and for 1 1 you are getting 0 as a output. So this is about the NOR gate, right? So like this manners, you can actually construct any combinational circuit, right? That could be a multiplexer, that could be any universal gate, okay, that could be any kind of gate with the help of this CMOS logic, right? Now tell me what similarity you can check here is. So now see, whenever there is a 0 alone, right? Whenever there is a 0 alone, so it is kind of A and B, right? So here you can see it is a 0 alone as it's a NAND circuit, right? It's a kind of A and B. And similarly now you can study here as it's a 1 alone, right? As it's a 1 alone, so A it's a and B, right? That means whatever the bit is alone, so this one actually you can represent a series combination, and rest of the combination for this 0 you can use the parallel combination, right? So this part actually we are going to study in the next lecture with different circuits and how to build the different combinational circuits with the help of CMOS logic design, right? So that part we are going to discuss in the next lecture. For today we will stop here. Okay, we will continue the discussion with the same combinational design using CMOS logic in the next lecture also. Okay, for till now you just remember these two gates. Okay, we have designed for NAND gate, also we have designed for NOR gate. Okay, so for today we will stop here. We will continue in the next lecture. Okay, for remaining part. If you have any doubt or query, you can ask me right now.
No doubt, sir.
Okay.